The wait is over. Today, you learn what Radians are. That annoying choice in your mode button on the calculators that if it's on Radians, all your answers are messed up. Well, in high school, you're going to need to put them on Radians most of the time when you're dealing with trigonometry. So you're going to have to know what a radian is. But to explain it, I'm going to give you the backstory on degrees. Degrees are just man made. All right, there could have been 100 degrees in a circle, or 1,000 degrees, or 10 degrees. Something that's a multiple of 10 or a power of 10 might have been, a little, had its benefits, might have been better, but maybe not. So let's see if I can explain where this came from. I think I've mentioned this in class before that there's approximately 360 degrees in a year, or sorry, 360 days in a year. And ancient civilizations, that's what they used for their calendar, was 360 days. So a lot of people think that's where it came from. But one of the first societies to have any record of mathematics and actually writing was in Babylon. Babylon, yeah, Babylon. So the Babylonians, and they were big into geometry, specifically equilateral triangles and hexagons, which makes sense because a hexagon is made up of 6 equilateral triangles if it's a regular hexagon. So I'm going to draw that inside my circle here. So I put the points on there, and then I'm going to connect those points. Now it just happens that, like I said, this hexagon you can make into 6 equilateral triangles. So if you connect each one of these vertices on your hexagon to the center, well, that's a radius of the circle, and it's also the same length as that side right there as the perimeter of the hexagon because it's an equilateral triangle. All 3 of those sides are going to be the same. They're all going to be the same length as a radius. 2 of them are a radius, and the third one, the outside of the hexagon, is the same length as a radius. And you may remember this from earlier in the year when we did constructions with the compass and the straight edge. We made a hexagon inside of a circle like this just by copying the length of the radius and then going all around the edge of the circle. So there you have it. A hexagon inscribed inside of a circle. Inscribed means it's inside the circle, but the vertices touch the circle. All right. The weird thing about the people in Babylon is that their number system wasn't like ours. We have 10 symbols for our numbers, 0 through 9. They had 60. Yeah, 60 different symbols. So they didn't get to a combination of their symbols until they got all the way to 60, whereas we combine our symbols when we get to 10. We use a 1 and a 0. I don't know what their symbols were, but they combined them when they got to 60. So they took this hexagon inside of a circle, and they figured since they had 60 numbers, they'd break each hexagon up into 60 little parts, and there's 6 of them. 6 times 60 is 360. So a lot of people think that's really where 360 degrees came from, was the fact that their number system had 60 digits in it. But it's like the chicken or the egg. What came first? Did they create a number system that had 60 parts in it because of this? Who knows? But that's kind of where it came from. So as you can see, it's man-made. The degrees, 360 of them, but it makes sense. It's a good number. It's stood the test of time. Another reason that it stood the test of time is that it's easily divisible into whole numbers. Like you can divide 360 by 2, by 3, by 4, by 5, by 6, and then all those numbers go into it evenly, whereas you can't do that with 10. So that's kind of nice. So you can divide a circle up into thirds real easily. They get 120 degrees each. If you try and divide 10 up into thirds, you end up with a decimal that goes on forever. That's kind of annoying. So 360 has its perks. But since it's man-made, people try to describe the size of a circle, the degrees of a circle, in a more mathematical way that's not man-made, and it's basically the relation of the circumference to the radius. All right. So they wanted to know how many, if you took a string that was the length of this radius and started wrapping it around the outside of the circle, how many times would it go around the circle? How many strings, the length of one radius, would it take to go all the way around the circle? Well, it looks like it's almost six. I mean, you got six sides of your hexagon here that are all the same length as a radius, so that's six of them. But just to get from this point to that point, the shortest distance between 2 points is a straight line. So if you wrap that string around the circle, now you're taking a longer route to get from here to here. All right, and that string is exactly that long, that straight line. So the longer route means you're going to need more than six strings, six radius to get around this circle. So at first, when I was reading this, I got excited. I'm like, well, maybe, there's a nice whole number. Maybe there's 7 or 8 radiuses that it takes to wrap around the outside of the circle, and we can do away with pi, and we can have something that makes a little bit more sense. Well, it didn't work out that way. It's not a whole number. It's not 7 or 8. It's actually how many radiuses does it take to wrap around the circle? It's 6.28. So it's definitely not a whole number. All right, and it's not even a very nice number. It's not divisible by anything readily apparent. But maybe you notice that it actually is. All right, if you notice 6.28, its significance, it's twice as much as pi. It's 3.14 times 2. So that can't be a coincidence that it takes exactly 6.28 radiuses to wrap around the outside of a circle. That is significant because half of that is 3.14, which is pi. So basically, how many radiuses does it take to get around half the circle to get from here to here? Well, it takes 1, 2, 3 plus a little bit more, because remember, we're not taking the shortcut. We're not going 1, 2, 3. We're going around the outside of the circle. So each one of these sections takes a little bit more than 1. And it actually takes 3.14, that's not writing very well, 3.14 radiuses to get halfway around the circle. And 3.14 is pi, so it takes pi radiuses to get halfway around the circle. All right, back to a better marker here. 3.14, oh nice. But we're not going to use 3.14, we're going to use the symbol pi. So how far is it to get halfway around the circle in terms of the length of the radius? Pi. Takes pi radiuses, 3.14 radiuses to get halfway around the circle, and 2 pi to get all the way back to where you started. And this is the birth, this is the basis of radians. Radians are labeled in terms of pi. So if you want to go 1/4 of the way around the circle, which would be if you start here, go up to the top, that would be half pi. If you want to go halfway around the circle, that's pi. If you want to go 3/4 of the way around the circle, that's 3/2 pi. 1/2 pi, another half pi, 3/2 pi, 4/2 pi. Every quarter circle is half a pi. So it takes you 4 half pies or 2 pi to get all the way back around to the beginning. Now, we're used to saying this is a 90-degree angle. So half pi is the same as 90 degrees. Pi is the same as 180 degrees. 3/2 pi is the same as 270 degrees. And 2 pi is the same as 360 degrees. So now you have radians. You have angles measured with pi as opposed to degrees. And that's a radian. So 90 degrees is the same as half pi. 180 degrees is the same as pi, so on and so forth. And that's radians. It took you 3.14 radians to get all the way to 180 degrees. That's pi radians. It only took you half a pi, which is like 1.5 0.57 to get a fourth of the way around the circle to get 90 degrees. So that's half pi radians. All right, and that's what your homework is going to be like tonight, is just converting degrees to radians. So, for example, let's say you have 120 degrees, and you want to convert 120 degrees to radians. Well, how far is 120 degrees on its way to, it's probably more like over here, 120 degrees? How far is that on its way to 180 degrees? Well, it's 120 over 180 reduces to 2/3. So it's 2/3 of the way to 180 degrees to a straight line. So 2/3 of 180 is what 120 is. So when it comes to the radians, it's got to be 2/3 of pi. So 120 degrees is the same thing as 2/3 pi. All right, 2/3 of 180 is 120. 2/3 of pi is 2/3 pi. So 2/3 pi is your radian measure. 120 degrees is your degree measure. Now, if you don't want to try and do that in your head and say, all right, 140 is what percent or what fraction of 180, and then multiply that by pi, there's a little formula that you can follow. So this is your formula. If you're trying to convert degrees to radians, you have to take your degree measure, which I'll just use 120 again. So you had 120 degrees, and you have to multiply it by pi over 180. All right, pi over 180 is the magic bullet here that converts degrees into radians. So 120 times this fraction would be numerator times numerator, denominator times denominator. You'd have 120 pi over 180, and 120 over 180 reduces to 2/3. So it's 2/3 pi, 2 pi over 3. So that's how you convert degrees to radians, and I'm just going to give you some random degrees, and you're going to have to turn those into radians, and it's not all that difficult. But if I just showed you this and said, okay, multiply these numbers by pi over 180, you'd be like, okay, I can do that, but you wouldn't really understand what you were doing. So hopefully this little history lesson here in this diagram makes it make a little bit of sense to you on why pi over 180 is multiplied by the degrees to turn it into radians.